Your kid logs bird sightings in the backyard, and 3 months later, those observations show up in a peer-reviewed migration study. That's not a feel-good story. That's how citizen science actually works, and it's quietly teaching your child the same data analysis skills that climate researchers and epidemiologists use every single day. My name is Lakshmi Venkataraman, and I'm a National Board-certified middle school science educator with a master's in curriculum and instruction. Welcome to the STEM Lab podcast. Quick note before we jump in, all the research, writing, and fact-checking you're about to hear is done by real human experts, but the voice delivering it is AI-generated, which lets us turn around high-quality content faster and keep episodes coming your way 3 times a week. If you've been listening for a while, thank you for being here. Your time matters, and I don't take it for granted. If you're new to the show, I'm really glad you found us. We drop new episodes every Monday, Wednesday, and Friday, covering everything from citizen science to coding projects to hands-on STEM kits. Today, we're talking about something that sounds abstract but is incredibly practical: how your kid develops real data analysis skills just by participating in citizen science. Let's get into it. When your child participates in citizen science programs focused on data literacy, they're not just collecting environmental samples or logging observations. They're developing the same analytical skills that professional researchers use in climate labs, epidemiology centers, and conservation biology field stations. I've watched hundreds of students transform from passive science consumers into confident data analysts through authentic citizen science participation. And the skill progression is remarkably predictable once you understand what to look for. So what exactly is data literacy in this citizen science context? It's the ability to collect, interpret, analyze, and communicate information from data sets. These are skills that sit right at the intersection of scientific inquiry, mathematical reasoning, and critical thinking. When we talk about the data literacy kids develop through citizen science, we're describing a specific competency stack that goes far beyond just doing a project. In citizen science contexts, data literacy means your child learns to design data collection protocols that minimize bias and maximize reproducibility. They use standardized measurement tools and recording formats that allow their observations to merge with global data sets. They identify patterns, outliers, and trends within their own data and larger community-contributed data sets. They evaluate data quality and recognize when measurements need recalibration or repeat trials. And they communicate findings using appropriate visualizations, statistical summaries, and evidence-based claims. Here's what makes this different from traditional science fair projects. In those, data often gets manufactured to fit expected outcomes, but authentic citizen science demands real-world data integrity. Your child's observations about bird migration timing through eBird or water quality measurements submitted to regional environmental databases actually matter. They contribute to peer-reviewed research, conservation policy decisions, and climate monitoring systems. This authenticity changes everything about how kids approach data collection. The technical infrastructure matters significantly here. Most modern citizen science platforms require internet connectivity for data submission, though collection happens offline. They operate through mobile apps on iOS 15 or higher and Android 12 or higher, or through web portals. And increasingly, they integrate with hardware sensors that require USB or Bluetooth connectivity. Understanding these technical requirements helps you scaffold appropriate projects for your child's skill level. Now let's talk about how data literacy actually develops through citizen science participation. The progression from simple observation to sophisticated data analysis follows a predictable learning path, and I've seen this arc play out consistently across different age groups and project types. The first stage, which typically happens between ages 7 and 9, is structured data collection. At this entry level, children learn data hygiene fundamentals, the disciplined habits that make scientific data usable. They're working with pre-designed data sheets, standardized observation protocols, and tools that constrain variables to manageable ranges. Concrete skills emerging at this stage include recording observations at specified intervals, like daily temperature readings or weekly bird counts. They learn to use measurement tools correctly and consistently: thermometers, pH strips, rulers. They follow sequential protocols without skipping steps, and they start distinguishing observation from inference. That's the difference between saying, "I see 3 robins," versus "robins prefer our yard." The National Geographic Birdwatching Kit exemplifies this level well. Check the link below to see the current price. It provides structured observation logs, binoculars with appropriate magnification for young users, and connection to the eBird citizen science platform, where kids submit sightings following standardized taxonomy. The kit requires no subscriptions, but does depend on adult-facilitated internet access for data submission. Stage 2, which happens around ages 10 to 12, is when data quality awareness develops. Middle elementary students develop critical evaluation skills. They start recognizing when data looks suspicious, understanding why calibration matters, and grasping how measurement error propagates through analysis. Capability milestones include identifying outliers and deciding whether to investigate or exclude them. They recognize when sensor calibration has drifted by comparing readings against known standards. They understand why sample size affects confidence in conclusions, and they document environmental conditions that might influence measurements. This stage benefits enormously from sensor-based citizen science using platforms like Microbit or Arduino. When your child builds an air quality monitoring station and discovers that their particulate sensor reads differently near the ground versus at table height, they're encountering real measurement challenges that professional environmental scientists navigate daily. The technical requirements shift here. You need USB connectivity for programming, stable Wi-Fi for cloud data upload. Most citizen science platforms don't support fully offline operation, and often external power supplies for continuous monitoring. Many families discover that choosing between Arduino and Microbit for citizen science becomes a critical platform decision based on their child's programming readiness and the specific environmental parameters they want to measure. Stage 3, for ages 13 to 15, is when pattern recognition and analysis really take off. Early adolescents develop analytical sophistication. They can work with spreadsheet software, generate meaningful visualizations, perform basic statistical calculations, and formulate evidence-based hypotheses from their datasets. Skills crystallizing at this level include creating graphs that highlight relevant trends, line graphs for time series data, scatter plots for correlations. They calculate central tendency measures like mean, median, and mode, and they understand when each is appropriate. They recognize correlation versus causation in their data. They compare their local data set against regional or global citizen science aggregations, and they formulate testable questions based on patterns they've discovered. This is where data literacy through citizen science truly mirrors professional research workflows. Students might analyze 3 months of water quality data from a local stream, graph dissolved oxygen against temperature, recognize an inverse relationship, then investigate whether the pattern holds across other citizen scientist submissions in their watershed. They're using Excel, Google Sheets, or increasingly Python with Pandas libraries, the same tools environmental consultants and research technicians use. Many sensor kits at this level require subscription access to advanced analytics dashboards or cloud storage beyond basic data submission. When you're looking at environmental monitoring kits, you'll want to check whether platforms charge for historical data access, API integration, or advanced visualization features. Stage 4, for ages 16 and up, is when experimental design and communication capabilities emerge. Advanced high school students achieve research independence. They design original investigations, control for confounding variables, and communicate findings using scientific convention. They're now capable of writing data collection protocols that others can replicate. They design A-B comparisons to isolate specific variables. They perform significance testing to determine if observed differences are meaningful. They create research posters or presentations formatted for science symposia, and they contribute to collaborative analysis projects with adult researchers. Students operating at this level often participate in programs like Zooniverse research collaborations, where they're not just collecting data, but helping professional scientists classify images, transcribe historical records, or identify astronomical phenomena within massive data sets. This scaffolds beautifully into undergraduate research preparation. The workflow of receiving training, analyzing assigned data sets, submitting classifications, and seeing how your work contributes to published research exactly mirrors what research assistants do in university labs. So why does data literacy through citizen science matter so much? The transferability of these skills extends far beyond science context. Every competency I've described above directly prepares students for career-critical capabilities across STEM and non-STEM fields alike. Industry-standard tool exposure happens organically through citizen science. When your 14-year-old learns to clean messy data in a spreadsheet, removing duplicate entries, standardizing date formats, filtering out incomplete records, they're developing the same data hygiene skills that business analysts, marketing researchers, and public health epidemiologists use daily. Environmental sensor calibration checklists for student scientists mirror the protocols that water treatment technicians and agricultural extension agents follow in professional practice. Authentic stakes transform motivation in ways that simulated projects never achieve. I've watched students who showed minimal engagement with traditional lab assignments become meticulous about data collection when they understood that their observations would help track monarch butterfly migration or document urban heat island effects. The psychological shift from doing schoolwork to contributing to real research cannot be overstated. Progressive skill building through citizen science creates natural on-ramps to advanced coursework. Students who spent 2 years collecting and analyzing environmental data arrive in high school AP Statistics or AP Environmental Science already comfortable with concepts their peers find abstract and intimidating. They've built schema around sampling bias, measurement error, and data visualization through lived experience rather than textbook definitions. Different citizen science domains develop overlapping but distinct data literacy competencies. Understanding these variations helps you select projects that align with your child's interests while still building the core analytical skills. Environmental monitoring projects focusing on air quality, water quality, or weather emphasize sensor calibration, continuous data collection, and time series analysis. Students work with numerical data sets, learn to identify sensor drift, and develop troubleshooting skills when equipment behaves unexpectedly. These projects typically require the most technical infrastructure: power supplies, weatherproof enclosures if sensors sit outdoors, and reliable internet connectivity for data upload. Biodiversity observation projects like bird counts, pollinator surveys, and phenology tracking develop classification skills, taxonomic precision, and spatial analysis. Students learn to use dichotomous keys, distinguish similar species, and understand how observer bias affects population estimates. These projects work well for younger students, ages 7 and up, because they require minimal equipment, often just binoculars, field guides, and observation logs, while still producing scientifically valuable data. Astronomy and space science projects, including meteor shower counts, light pollution mapping, and aurora observations, build pattern recognition across large data sets and statistical thinking about rare events. Students confront questions like, is this meteor shower more active than last year, or did we just have clearer weather? That naturally introduce concepts of variance and confidence intervals. These projects often require specialized software for data submission and may involve late-night observation sessions that need planning around family schedules. Crowdsourced analysis projects focusing on image classification, audio analysis, and historical document transcription develop attention to detail, classification consistency, and quality control awareness. Platforms like Zooniverse provide training sets where students receive immediate feedback on their classifications, building calibration between different observers. These are excellent for developing data literacy skills entirely screen-based, which is useful for families without access to outdoor spaces or specialized sensors, though you'll want to balance screen time appropriately. Each variation connects to different career pathways. Environmental monitoring prepares students for work as environmental technicians, water quality specialists, or agricultural scientists. Biodiversity work scaffolds toward wildlife biology, conservation ecology, or environmental consulting. Space science projects build foundation for astronomy, remote sensing analysis, or data science more broadly. Let me tackle some questions I hear frequently about this. What age should children start participating in citizen science projects to develop data literacy? Children can begin meaningful citizen science participation as young as age 7, starting with structured observation projects like bird counting or weather recording that teach data collection hygiene and measurement consistency. The key developmental marker is the ability to follow multi-step protocols consistently and record observations without adult prompting for each entry. More sophisticated data analysis skills, graphing trends, calculating statistics, identifying outliers, typically emerge between ages 10 and 13 as abstract reasoning develops, though you can scaffold these capabilities earlier through guided questioning about patterns in their data. Do citizen science projects require expensive equipment or ongoing subscription costs? Entry-level citizen science requires minimal investment. Many biodiversity observation projects need only field guides, basic recording materials, and internet access for data submission, with no ongoing costs beyond your existing connectivity. Sensor-based environmental monitoring projects do require initial equipment investment, typically $50 to $300 for quality sensors, depending on parameters measured, and some platforms charge subscription fees for advanced data analytics or historical data access beyond basic submission, though many educational-focused platforms offer free tiers for student scientists. The most important cost consideration is consumables. Some water quality testing kits require replacement reagents or test strips, while air quality sensors need periodic calibration against known standards. How does citizen science data literacy transfer to school science classes and standardized testing? The analytical skills students develop through citizen science, designing fair tests, identifying variables, interpreting graphs, evaluating data quality, drawing evidence-based conclusions, directly align with next-generation science standards performance expectations and appear extensively in state science assessments and AP science exams. Students who've collected and analyzed real environmental data consistently outperform peers on questions requiring data interpretation, graph analysis, and experimental design because they've encountered these concepts through authentic problem solving rather than just textbook examples. The gap becomes particularly visible in constructed response questions where students must explain their reasoning about data quality or experimental controls. Can citizen science projects work in apartment settings without access to outdoor spaces? Absolutely. Many high-value citizen science projects operate entirely indoors or from windows and balconies, making data literacy citizen science programming accessible regardless of housing situation. Indoor projects include classifying astronomical images through Zooniverse, transcribing historical weather records, analyzing audio recordings for wildlife calls, monitoring indoor air quality, which is particularly relevant in urban environments, tracking sunrise and sunset times and day length from a window, or participating in great backyard bird count observations from a balcony or window feeder. The analytical skills developed through these projects, pattern recognition, data quality evaluation, statistical thinking, are identical to those built through outdoor environmental monitoring, and the data sets often contribute to equally important research questions. What's the progression from beginner citizen science to research-level data analysis? The learning path typically follows structured data collection with pre-designed protocols for ages 7 to 9, then recognizing data quality issues and understanding calibration for ages 10 to 12, then creating graphs, calculating statistics, and identifying patterns independently for ages 13 to 15, and finally designing original investigations and contributing to collaborative analysis for ages 16 and up. This progression mirrors how professional scientists develop expertise, starting as field technicians following established protocols and advancing toward independent research design. Students who maintain consistent citizen science participation across this arc often arrive at undergraduate research opportunities already comfortable with literature review, data management, statistical software, and scientific writing conventions that their peers encounter for the first time in college. The pathway from citizen science through building machine learning models represents one particularly relevant progression, as environmental monitoring datasets increasingly feed machine learning applications for pattern detection and prediction modeling. Data literacy kids develop through authentic research participation represents one of the most efficient pathways to building career-critical analytical skills. Unlike isolated classroom exercises, citizen science embeds data collection, quality evaluation, pattern recognition, and evidence-based reasoning into meaningful contexts where your child's work contributes to real scientific understanding. The progression from simple, structured observation through independent data analysis follows predictable developmental stages, with each level building concrete capabilities that transfer directly to advanced coursework, standardized assessments, and professional STEM workflows. The infrastructure requirements vary significantly by project type. Simple biodiversity observation needs minimal equipment, while sensor-based environmental monitoring demands careful attention to power requirements, connectivity specifications, calibration protocols, and potential subscription costs. Starting with how to choose a citizen science kit for your child's skill level helps you match technical complexity to your child's current capabilities, while keeping an eye toward the practical logistics of starting your first project. What makes this approach particularly powerful is how it builds genuine research habits, the disciplined attention to measurement consistency, the intellectual honesty to recognize when data doesn't support your hypothesis, the systematic thinking to isolate confounding variables. These transfer seamlessly from backyard weather stations to professional laboratories. Your 10-year-old logging daily temperature readings is developing the same data hygiene that climate scientists rely on for multi-decade trend analysis. That's not aspirational thinking, that's the documented reality of how data literacy develops through authentic practice. That wraps up this episode of the STEM Lab podcast. Thanks for spending this time with me today. New episodes go live every Monday, Wednesday, and Friday, so there's always something coming down the pipeline. If you found this episode valuable, I'd be really grateful if you could leave a 5-star rating and write a quick review. It sounds small, but it genuinely helps other parents and educators discover the show when they're searching for practical STEM guidance. And if you haven't already, hit subscribe or follow so you get a notification the second a new episode drops. I'll see you next time.